Gators. This is 6.4, the fundamental theorem of calculus and accumulation functions. On the last lesson, we learned about the definite integral, which this integral represents the area under the curve of f of x on the interval from a to b. Let's say we know the intervals start at a, but we don't know where it stops. That would give us an interval from a to x, where a is a constant and x is some unknown variable. We can represent this new function, and it looks like this. Capital F of x is equal to the integral from a to x of f of t dt. Now, I want to make you understand that you have seen other functions. These are other functions that you have. This is a brand new function, and it requires that you put input values so that you can get output values. This is an area accumulator function. It's described as capital F of x to distinguish it from the function f of x, which is being used to find the area under. Okay, let's take a look at this area accumulator function and actually go through input values and find output values. So I'm trying to find the area from 0 to x, and if I find the area from 0 to 0, I will get 0. I don't get any area. You're not going anywhere. If I want to find the area from 0 to 1, the area under the curve happens to be -1. If I want to find the area from 0 to 2, I'm accumulating -2. If I want to go from 0 to 3, I'm accumulating -3 area from 0 to -3, or to 3. And 0 to 4, I'm going to be accumulating -3.5. And when I accumulate area from 0 to 5, notice I'm going to get some positives, so some of that negative is going to cancel out, so that's -3. And then I'm going to acquire some more positive area, and that'll be -1.5. So this will be -1.5. I'm acquiring more positive area, so that'll make that a 0. And then acquiring some more positive area, which is a half. Now I'm going to graph all of these: 0, 0, 0, -1, 2, -2, 3, -3, 4, -3.5, -3, 1.5, 0, and a half. So here are all my points. Let me go ahead and draw a function, and we get this. And notice that this is acting like an antiderivative. Remember, all of these values are negative, which represents this decreasing idea. It goes from negative to positive, which tells me that this is a minimum, which it is. And all these values are positive, and notice that this is an increasing function. Let's re-examine the same curve, but start at a different place. And so now I'm going to start at the number 2. And starting at the number 2, I go from 2 to 2. I'm going to have 0 area. So this is going to be 0. And then going from 2 to 3, the area under this curve from 2 to 3 is going to be -1. The area from 2 to 4, is going to be -1.5. And then I'm going to, that's -1.5. Then I'm going to acquire some positive area here, which is going to cancel out some of this, so that's -1. And then I'm going to add some more positive area, so this is going to be a 1/2. And then I'm going to add more positive area, 1.5, that's 2. And then add more positive area, which is 2.5. Now when I graph all these points, I have this curve. This curve looks a lot like the other curve, but it is now translated up, all right? But I still get the same minimum look. I still have decreasing on the same side and increasing on the other side. So this tells us that this accumulator function is really an antiderivative. All right, now we're going to do the fundamental theorem of calculus, which says that when you take the derivative of an antiderivative, because that's what this area accumulator is, then it is really just the function. They're undoing each other. And the way I'm going to do it is I'm going to approach it like I've done all derivatives. I'm going to take the limit of the difference quotient. I'm going to take the change in the y's over the change in the x. But this is for the area accumulator function. So here is the area from a to x, and from a to x plus h. And so if I take the difference of these two areas from here to here, I'm going to get this red area, this little red area right here, which is the difference between the two areas. And h is small. We can also figure out this area right here, which is this red area, can also be described with a rectangle, which is the base and the height. So the base and the height right here. Now these are approximately equal to each other because this rectangle isn't quite equal to the area under the curve, but it's close. And what I'm going to do now is I'm going to divide both sides by h. And when I divide both sides by h, the f of x is approximately equal to this different quotient. Again, approximately. To make it exactly equal to it, I would have to take the limit as h approaches 0. And as h approaches 0, I will get this f of x, which represents the derivative of this area accumulator. So the idea of a derivative of an antiderivative being the function is what the first fundamental theorem of calculus says. So the derivative of an antiderivative is the function. Let's talk a little bit about the notation, and let's make sure you understand what's going on. The derivative is with respect to x. And so x is the variable I'm taking the derivative of. Notice that there is no x in the integrand. In the integrand, we use what we call a dummy variable. That stands for the heights and widths of all the rectangles that are being accumulated. We don't want this to have x because the emphasis is the variable is up here in the upper limit here. Derivatives and integrals are inverses of each other. They cancel each other out just like multiplication and division. This capital F of x is considered the antiderivative of little f. All right, let's go ahead and practice. So the derivative of an antiderivative is f of x. So if I want to take the derivative here, remember this is f of x right here. So, and it's in terms of the dummy variable. This is the variable right here. So when I take the derivative, it will be the function back. So f prime of x will be equal to this function, but make it in the variable x, not the variable t, because that's our variable function. All right, let's take a look at something a little bit more complex. What happens if the upper limit is not just a simple variable x, but it is a composite? And if this happens, then we're going to be taking these two undo each other. We are going to have this function, but this function is a little bit more complicated because it has this inside of it. And so it's going to be f of g of x, and because this is a composite and we've taken the derivative of the outside, we must take the derivative of the inside. So on this problem, f prime of x, remember here's the function right here, and we're going to insert this function inside, and we have just found the derivative of the outside, because taking the derivative of the outside of an antiderivative is just the function itself. But because this was a composite function, we have one more step, and we must take the derivative of the inside. Let's go ahead and do this. Remember, this is the function, and this has to be inserted inside here. So the derivative is, the undoing process is just the function, h of 4x, okay? So they undo each other. We just get this guy back, but with this inserted in it, and then don't forget to times by the derivative of the inside. Let's take a look at something a little bit more complex where the upper and the lower limits are both functions. We're going to do the same thing that we just did a few minutes ago for the upper limit, and we're going to do the same thing for the lower limit. We're going to be subtracting them. The subtraction process I will be talking about in the future, why it's subtracting and nothing else. All right, so this is going to be f prime of x equals, now they're going to take the derivative, so this is going to be inserted in here. That's pretty what we were doing at the very beginning. So this is going to be 5x, and then we're going to write minus, and then we're going to insert this inside of that, so that this is 5 times negative x. But because this is a composite, we have to times by -1. And if you want to simplify this will be minus 5x, and then this will be equal to 0. So the derivative is equal to 0. Over here, f prime of x, and again, you want to keep the same function, but you want to insert this inside everything that's a t. So let me go ahead and do 3x squared minus 3x, and then minus, and then I'm going to insert the 2x into these. So then this is 2x squared minus 2x. And I forgot something, okay? And I forgot to take the derivative of the inside. So once I insert here, I forgot to take the derivative of the inside, which is times 3, and then I'm going to have to times this by 2. So this answer will be equal to 3 times 9x squared minus 3x minus 2 times 4x squared minus 2x. Okay, which is a common mistake. And this is the end of the screencast.